So we have a second talk by Mazi Jalaal on droplets of yield stress fluids. Mazi got his PhD at the University of British Columbia in 2016. He was then a postdoc at the Physics of Fluids group at the University of Twente, and that was followed by another postdoctoral position at Cambridge. Recently, he's become an assistant professor at the University of Amsterdam, and his research interest is on a broader context, is in complex and biofluids using combination of theory and experiments. Okay, Mazi, over to you.
Thanks so much, Sophia. Great to be here, and thanks for all the organizers of this Friday afternoon talks and the George Batchelor conference. So I'm going to talk about viscoplastic fluids, also in the context of films and coatings. In fact, there are, as been discussed already, there are many methods of coatings fluids on the surfaces. One of them, as I'm showing here, is inkjet printing, for instance, that when you put droplets one by one on top of each other, I will get back to it later, but also more classical methods of coating fluids on top of surfaces, like deep coating, where you get a plate that you want your liquids on it, you dip it in the fluids and you take it back. Typically in the industry, you do it multiple times, so you get a very smooth coating of your fluids on it. So my talk today is very relevant to the process of coatings, but what really drives me or drove me in the past few years to do this research is the industry of 3D printing and the applications to 3D printers. Here I'm showing 4 examples, being plastics, clays, foods, and biological 3D printers. And I'm only showing a particular type of 3D printers that are basically based on extrusion. These are also called fused deposition type of 3D printers. So what you can see is in most of the applications, the fluids that are used are not actually Newtonian. In fact, you need some sort of non-Newtonian behavior like yield stress to keep this 3-dimensional structure for your object that you're 3D printing. If you don't know how 3D printers work, this is a picture I typically use to explain them. So to make a 3D printer, this type based on extrusion, all you need is a pressure source, a nozzle, a viscoplastic material or non-Newtonian fluids that I come to it what it means to basically go through your nozzle, and a substrate that can be soft or hard that you basically 3D print on it. So what happens in most of the 3D printers out there, instead of the hand in this picture, you replace that with a robotic arm, and you give the digital information to the robots, and the robots print whatever you want. So here is an example with a non-Newtonian fluids again. It's 4 times it's filled up, and what you do, you basically start, your robot goes around, deposit your materials on the surface, and after the first round is over, you go another round and you start depositing the second layer, and the more you put on it, you basically get a 3D printing, your 3D print your structures, basically. Okay, so motivated by this, we try to simplify this problem to a much simpler problem, in fact. And here is what we studied this in the context of a spreading. So the problem, that what I call the simplified problem, as follows. So you have a surface, a solid surface that is pre-wetted by a film with a thickness h infinity. And at time 0, you deposit this bigger droplet that the length scale or the characteristic length scale is much bigger than this film thickness, and you let it go. So if your fluid is Newtonian, nothing stops this droplet to spread, right? So the surface tension and gravity let it spread, and this droplet spreads forever until you get this flat surface. That being said, there is a lot of technicality, especially in the small length scales associated with this problem, in particular when your capillary number goes over 1. Last time I actually gave a talk in Friday afternoon in DAP. I talked about only the Newtonian problems of this simplified spreading problem, but the work is published now in JFM, so you can have a look. What I'm going to focus is actually this non-Newtonian fluids. As I showed you, most of these fluids in 3D printers are not Newtonian. And the type of fluids that I'm going to talk are called viscoplastic fluids or yield stress fluids. So if I want to put it very simply, what these materials are, they have microstructures in them. And these microstructures in the macro scales emerge to this behavior that below a critical stress, your materials look more like a solid. And above that, your material looks, if you put enough stress on it, your material starts to flow. So you can think of toothpaste, for instance. Toothpaste doesn't flow if you don't do anything with it, but if you push enough, it starts to flow, basically. So how does it look like mathematically? I mean, if you look at this so-called flow curve, where you have a shear rate in the x-axis and a stress on the y-axis. For a simple Newtonian fluid, this is a straight line going from the origin, and the slope of that line is the viscosity. But for this yield stress materials, you have this offset in the stress axis. So below that, you don't get any deformation. And above that, for this simple case of Bingham fluids, you have constant viscosity, but typically the viscosity above yield stress is also non-linear. Okay, in a tensorial form, you can write it as below. So again, the stress is below the yield stress, no deformation. Above it, you get flow. Okay, so if I go back to the problem that I just showed you, nothing has stopped the Newtonian droplet to spreads, but if you have a yield stress, at some point stress inside your droplet falls below the yield stress, and therefore you approach this final shape. So this final shape gonna have two characteristic lengths, this radius of your droplet and also the height. So I am noting them by RF, final radius and final height here. And we're gonna try to answer two questions. First of all, how this viscoplastic droplet spreads on the surface in this problem, and what is the final shape? And the final shape is in particular important for us because if you think, for instance, about 3D printers, the final shape or final radius is the resolution of your 3D printers. Okay. All right. So we tried to tackle this problem multiple ways, but I'm going to start with the simplest way, which is giving a scaling law for this final shape. All right. So imagine you have this droplet, it spreads, and at t infinity, it reached this final shape. And so this droplet has a volume V, and this volume V has a characteristic length scale L that we define this way. Basically, if this wasn't a sphere, L was the radius of that sphere. When it reached this final shape, if you assume this is shallow and hemispherical, this volume is proportional to final height times the square of your final radius. And now you can start balancing forces to see what are these final radius, for instance. All right, so if you have pure capillarity, so the only thing that drives this spreading is capillary forces. So for instance, your droplet is so small that gravity doesn't do anything. So what I can do is that I can balance my capillary forces, surface tension times curvature times a characteristic area, with the yield stress forces. Imagine that my yield stress is doing most of the work at the bottom of this droplet, okay? And for this given volume, I can immediately reach this scaling law. So what is it? Let me walk you through it. So RF, my final radius, normalized by the characteristic length scale L that I'm written here, is equal to a prefactor gamma c times this number to j to the power -1/7. So it is a weak dependency to this non-dimensional number. What is it? It's basically a number that has been named, what we like to call it is basically a plastocapillary number that compares plasticity or yield stress with the surface tension. Okay, so basically what it says, as yield stress goes up, your material becomes stiffer, the J value goes higher, therefore your final radius is smaller. So this is the regime of, again, plastocapillarity. Only plasticity and capillarity are important. Another asymptotic regime will be when gravity is the dominant force. So you now can think about geophysical applications when gravity is the main driving force of a spreading. Then you can write gravity force and balance it with the same yield stress forces, and you immediately get such a scaling, which has been known previously, in particular for the applications like cement rheology. So what it says is basically the final radius now goes to such as this. There's again another prefactor, and now this new number shows up, B, which is the bone number that compares gravitational force and capillary forces. All right, so you should note that there is no surface tension actually in this equation I highlighted by red. I just wrote it this way to be consistent with what I have. Okay, so there are these prefactors, and we can search for that prefactor in multiple ways. And what we've done initially was to go to lubrication theory. So lubrication theory is basically thin film equations when you have a thin film with a profile H here, and under gravity and capillarity, you assume the height of the characteristic height of the film is an order epsilon smaller than your horizontal length scale. So this is very shallow. Your velocity profile looks like this, and you start from Navier-Stokes, you simplify your equations, you end up to this single differential equation that is known as evolution equations or lubrication thin film equation. Okay, so I listed just a selected number of people that extensively worked on these equations. If I want to briefly tell you what it is, so H is the film height, and the left-hand side is the variation over time. And on the right-hand side, I have the pressure gradient, so P over R, that has gravity term, so bone number times H, and this higher order derivatives comes from the curvature of your system. Okay, and H cubed is like a diffusive term. All right, so you can solve this, but our problem, as I said, is not Newtonian. So what that means when we have yield stress fluids. So if you have yield stress fluids, such a situation can happen. So you can have a situation in which the stress below a point that I'm showing here with a plane Y is larger than your yield stress. So you start yielding the fluid, but above it, the stress is actually below the yield stress, so you get plug-like flow. Okay, and that will change your equations. And if you do the math, you end up to an equation that looks like this. So again, you have all the terms that you had before, but your H cubed term is now modified to Y squared times this term, and Y again is called the yield surface. That's exactly where stress is equal to the yield stress. Okay, and it's defined like this. So let me tell you some limits. If Y is equal to H, so this yellow line goes all the way to the blue line, that's where I'm yielding everything. So my fluid is like a viscous Newtonian fluids, and you can see it here. So if Y is equal to H, therefore you get back your H cube, and that's a Newtonian thin film equation I just showed you before. But if Y goes to 0, that means that everything is plugged in the thin film. That means nothing moves. And later I'm going to actually use it to find my final shape, because my final shape is when nothing moves, meaning Y goes. Okay, so you can solve these equations with any numerical methods you like. We did it with the final difference method. And here's an example for 0 bone number, means gravity doesn't do anything. And it is basically simply only driven by surface tension. So your droplet spreads from this initial condition, it goes all the way, and over time it approaches this final shape that I also highlighted by the gold line. Okay, and just to give you an example of how the yield surface looks like for this, I chose this one, this particular time that I'm showing with blue. Blue is the surface of my droplet, and this dashed line in red is my yield surface. So what you can see in this picture is what happens at the edge of this droplet when the droplet merges to the thin film. And what you see is this sort of undulations along the line. Such undulations are very well known for Newtonian fluids. If you look at the literature on thin films, but here we also see them for the viscoplastic case, and interestingly, they're so persistent that they actually stay in the final shape of your viscoplastic droplets. This could be important if you're in the application very thin films or very small features are important. Okay, and mathematically is also extremely important for us because that defines our boundary condition when we try to solve this equation asymptotic. I get back to it in a minute. Okay, so as I told you, I can solve this equation fully, but if I want only the final shape, all I need to care is basically this y equation. So y goes to 0, there's no flow, everything is plugged up, therefore I get my final shape. So this is also a differential equation by itself, right? H minus J, because PR is my pressure derivative. So let me open it up for you. So this is the full equations. All equations I showed you, by the way, is in axisymmetric coordinate and polar coordinate, but you can easily write it for 2 dimensions. Okay, so this is my equations. I have this third order derivatives on the left. The gravity terms is there too, and then I have this switch between the sign of H going above or below my pre-vector terms. And here is a solution of this equation that I'm showing with dashed red, and the white line, which is basically just on it, is a perfect match with the solution of the full lubrication equation via finite difference. No surprise that they're matching, because in principle they are the same equations. Now I can zoom in also here in the at the edge, and here you can see these undulations for the final shape that I'm solving, and the sawtooth curves that you see is the second order derivatives of the profile. And why I'm showing this, because we had to deal with these features at the edge to get the proper boundary conditions when we solve these equations. All right, so what I don't show you now is basically we first had to prove these undulations accumulate at some point, because in Newtonian case, they go forever, right? So the wavelength is constant, the amplitude exponentially decreases, but they never vanish. But here, we actually show that these small undulations vanish for the case of yield stress fluids. And then in that accumulation point, we find the boundary condition, therefore we are able to solve. Okay, so you can do a lot of these asymptotic solutions. So why this is very useful? Because I can now go back to the scaling law I showed you in the beginning. Through these asymptotic solutions, I can find my omega, my prefactor. So I put all of them in this one curve. So omega is my prefactor in this scaling law. And if you know your bone number, if you know your pre-vector film thickness and the mechanical properties and surface tension of your fluids, you can come to this box, choose your omega. So for instance, I don't know, you know your yield stress, surface tension, everything. You come here, you find your omega, therefore you can predict your final radius of your droplet. Okay, so there are two interesting limits. One is that if you have pure surface tension to drive your droplets, and therefore you get the final radius, the prefactor is 1.74. And the other one is the pure gravity. Pure gravity is much nicer because you only have to deal with first order derivatives, so you can solve it actually analytically. Okay, so this is nice. We have some theoretical analysis. The main questions comes, is this correct? And the only way to know is to do experiments. So this is our experiment. It's extremely simple. We had the camera, we had diffuse light on the other side, and we took a nozzle next to a treated glass substrate to deposit these droplets on it. So the reason we had to treat the glass, we chemically treat the glass, was that these polymeric materials are also very good to slip on the surface because of elastohydrodynamic interaction. But we removed that, so we are able safely to compare it with our theory. If you're interested in slip of these polymers, here's our paper. Okay, we use Carbopol solutions for our spreading. These materials, rheological behavior look like this. So what I'm showing on the left is G prime, elastic module, and G double prime as a function of a stress imposed on them. As you can see, is that below this critical yield stress, which is around 11 here, the materials look more like a solid plastic solid. It's a viscoelastic material, but it looks like a viscoelastic solid. But above that, it's suddenly everything starts to flow, and you have a weakly viscoelastic liquid. Okay, and above the yield stress, you can look at the flow curve, and you will see this is Herschel-Buckley, meaning it doesn't have, it has yield stress. It also is shear thin. You can tune easily your rheology by by basically changing the polymer concentration. And we made multiple samples to test like this. So we basically take the nozzle, close the surface, we pump the liquid, and we stop the pump, and the liquid spreads. Everything is very slow. This is a speed up video. And what will happen is that you get results like this. So from top left to bottom right, I'm showing you the final shape of droplets for different yield stresses. So as yield stress increases, your droplet spreads less. Okay. So is it good when I compare it with our asymptotic analysis? So I'm going to put everything in this curve. So on y-axis is my final radius, normalized by the characteristic length scale from the volume, and the x-axis is this plaster capillary number that I have. The larger the value of J is, means that the larger the yield stress effects. So lines are my asymptotic solutions, and dots are my experimental solutions. So there are some very good signs, meaning that first of all, our experiments match really well to some extent with our power law or scaling laws that we found from the theory. But when you look at it, it looks like that asymptotics are overestimating the experiments. And I'm not going to go to the details, but these experiments have a lot of challenges in terms of space parameters, of the controlling parameters. But when we first look at this curve, we wondered, is this mismatch coming from our theory being asymptotically only for shallow droplets, right, for the lubrication one? And can we actually fix that? And the first thing came to mind was, let's go to the lubrication theory and start solving the full momentum equations. So momentum equations are like this, continuity equations, momentum equations. That the main difference is that my stress tensor here is now different because I have all these rheological effects. Okay, so the way the stress tensor is basically for a so-called Bingham model is like this. Again, as I said before, below the yield stress there is no deformation, and above the yield stress I get the flow. But to be able to implement easily these rheological effects, we use the regularized version of this. So it means basically this. What does it mean? Basically, instead of having no deformation, I'm using a very, very large viscosity. So I regularize that parameter. So this introduced me a regularization parameter, which is, you can think of it as a ratio of my plastic viscosity to the mu max, what I'm showing here in non-dimensional form. By the way, it looks like this. So you can think of, there is a Ohnesorg number, a very large Ohnesorg number. One should be very careful when using regularized methods to show that your simulations are independent of this parameter, and that's what we've done. Okay, to solve this equation, we use the open source codes Jerry's and Basilisk, both of them developed by Stephen Popney Institute and Ambert in Paris. Excellent tools, and we use that to basically implement this Bingham model in it and solve these equations. So I'm going to show you one example only. So this is a case that there is no gravity. So in panel A is almost my initial condition. Droplet is sitting on it. The color is the log 10 of my the second invariant of the shear rate tensor. So what does it mean? It means that whenever it's white or very bright, I have a lot of deformation. Whenever it's going black, it means I don't have much deformation. So at time 0-ish, I have a very high curvature here. I'm deforming a lot of fluids, and I'm pulling basically somehow the fluid from the contact line. And as time passes, now with solving the full equations, I can look at the anatomy of my flow inside the droplet in much more detail. So something that you can see is that there is this low deformation zone at the center of the droplet. So that somehow resembles this static plug region. But over time, you also get another low deformation zone at the interface, which somehow you can think of it as a plug-like, moving plug-like region. But what is very important for us is as time goes to infinity, at some point everything is black, meaning nothing moves. Okay, and that's my final shape. So I can extract final radius here and put it back in the curve I showed you before. So here it is. So here is all the asymptotic simulations and experiments together. Blue symbols are my fluid equation simulations, and interestingly, they really match very well with asymptotic solutions. We again can think of that this scaling seems to be correct, but still there is some discrepancy with experiments that we have some ideas. For instance, when J is very large, that means that the plastic effects are very important. Therefore, how you deposit droplets become important because you're not yielding everywhere. Right? All right, so to put everything in a nutshell, these equations probably do it. So that is the final radius of such droplets as the scaling law for the final radius. And now this prefactor omega is known via experiment, simulations, and also asymptotic simulations. Okay. So a little bit of outlook in the next 2 minutes, that where we go from here. So what I showed you, basically your droplet, the larger the yield stress, the smaller the radius. So one of the questions came to our mind was that can we use this to somehow make a smarter printers or coating method? So can we use yield stress as a control parameter for the final radius of the droplets or not? So this is something that we've done using this so-called thermoresponsive polymers. These are solutions that become yield stress as you heat them up. And we show that when you have a spreading droplet, if you turn them, you can basically use this yield stress feature, make them to become yield stress, therefore stop them at the moment that you want. You can think of it as again, in the 3D printing or printing language, that you can define your resolution with heat, in fact. We also looked into can we get rid of nozzles in printing yield stress materials, because there's always this in industry, this problem with nozzle cloggage. And one of the works that we've done was we used lasers in this technique called laser-induced forward transfer to, instead of pushing the fluids through a nozzle, to shoot laser to our viscoplastic materials and make a jet, and therefore harvest this jet to print. Okay, so I stop here for the sake of time, and I just want to end the talk by thanking my co-workers, in particular Neil Bamford and Boris Stober. Almost everything I explained today in this talk was in collaboration with them. The few slides in the end about laser printing was also in collaboration with colleagues at Physics of Fluids Group in Netherlands. And thank you for your attention. I would love to take any questions if there's any.
Thanks a lot, Mazi. Very interesting talk. What's the concentration of the suspension? I guess you have a variety. Concentration of the suspension.
Yes, I don't remember the exact value, but these are very low concentration materials. So I guess less than 1% is enough to make your fluid viscoplastic with a yield stress around orders of 10 Pascal. So around 1% of your polymer is enough to make it. But I forgot the exact number, to be honest.
Yeah. Second question, how to measure the physical parameters of the liquid, shear stress and shear strain of the liquid?
So if your question is around something like this, these are rheology data. So you can use classical rheometers, and these are shear rheology data. So any technique works fine with this material. So, plate and plate, cone and plate, and you deform them on multiple or different shear rates. You read out the stress, or the other way around. For elastic properties, you typically do oscillatory test, a small amplitude, though you can do large amplitude if you're interested. Okay.
So now that we are on physical parameters, maybe I can ask a question. How do you measure surface tension of yield stress fluids?
Yeah, we can't, if I answer in short. So that's an excellent question, and it's a challenge. So there are attempts in the literature to measure the surface tension. In short, if I want to say, all the techniques, all the available experimental techniques for Newtonian fluids somehow fail for yield stress fluids, because like pendant droplets, you can't make a pendant droplet with hair gel or I don't know, toothpaste, right? They keep their shape when they come off the nozzles. There are some of the methods proposed are basically between two plates, for instance. The one that I'm a bigger fan is when you use extension jets, like methods like Cabr, but now with viscoplastic fluids, because during the breakup of the jet, when you extend them, you can think that yield stress is not, also elasticity is not that important. So that's the closest to surface tension. But I think that area needs more attention to measure surface tension.
Just because also the comparison between the modeling and the experiments probably.
Exactly. Exactly. So the curve I showed you as a comparison, it's very sensitive to the value of the surface tension. So I didn't measure the surface tension value myself. I took an average of what is available in the literature. And if you change it by a few percent, I can actually match very well between experiment and theory. But that could be one of the reasons, in fact. But we left it as it is, as an open question for future.
Okay, going back to the questions in the chat, is there an equation about the yielding region shape?
Yes. So maybe I went too fast on it, but the Y here is the so-called yield surface. And if you solve these equations, basically you get where your yield surface is. And that's what I try to show, oh, not here, but here. So if you look at the blue line, that's a profile for an arbitrary time while the droplet is spreading. And the dashed red line is my yield surface. So that's exactly where stress is equal to the yield stress. And you can solve those equations by finite difference and get it. So go back to the equation. So this is the equation for the yield surface. If you're asking about the lubrication theory.
Next question, what's the role of normal stress in the final radius value?
I don't know. That's an excellent question. In general, the other rheological effects, such as normal stress elasticity in general, this is not known to us very well. What are those effects to the final shape? I can give my idea, which is a hypothesis, that I don't think elasticity plays a significant role in at least from the comparison between our inelastic material and experiments. Yeah, I mean, I can't say much more than that. What one can try to vary the normal stress of the fluid, spread them again and see how much it changes. I won't be surprised if it does change. It's something, including the other effects like normal stress, is a great extension to this work, which we haven't done actually.
Okay, next question. What's the time scale of spreading, and does the radial spread against time behave the same way as the Newtonian fluids until it spreads?
Yeah, that's also a very good question about dynamics. So yes, I have. So in the experiments, these are a few tens of seconds. If you're thinking about lubrication, I guess I have, yeah, so here I have a slide. So here is the radius of this lubrication solution over time for the case when bone number is 0. And as you can see, so this straight line here is basically Newtonian droplet spreading, and you get this famous Tanner law that they spread with a prefactor 1/10 over time. And if you have a viscoplastic liquid in the beginning, because you're somewhat yielding everything, yield stress effects are not yet important, you get this Tanner law, but over time you deviate from it and you go to this final shape base. Experimentally, the time scales are a few tens of seconds. We try to do the experiment in a quasi-static form that droplet very slowly spread on the surface. So we don't want to put a lot of stress on the droplet. So we do it very, very slowly, in fact.
Do you expect physically to have the precursor film made of the yield stress solution or only the solvent of the fluid? Would it change anything in the analysis or is it not important?
That's an excellent question. And I think the question comes from the fact that many people also propose pre-wetted film or precursor film as a method of removing contact line singularity. Which is also was one of the reasons we also use pre-wetted film to get rid of the complexity associated with contact lines. If in reality, if I have a droplet that I put it on the surface and if it does makes a precursor film or not, we don't know. We have no evidence of it yet. And what is that precursor film? If it does form, we also don't know physically. It could be only solvent. You're right on that. The problem we solved is kind of different approach. We basically defined that this precursor film is from the same material because there are many applications like a spray coatings or 3D printing that you deposit the material on the same type of material. So our approach is slightly different, but if you're thinking about precursor film, also open questions there that we don't know at this point.
In the experimental picture, the top part of the drop seems to have a plateau and doesn't look round. Is my observation wrong or right? If this is right, do you have any idea why it's such a shape?
I guess these are the experimental results, and if you're referring to these tiny things coming up here, that's because of my nozzle is slightly wetting the liquid is slightly wetting the nozzle. So if you're talking about these things, however, it's a common feature of viscoplastic droplets, especially when they're large. If they're a small, surface tension flattens the surface. It's strong enough. But if they're thinking about large viscoplastic materials, you always get this tip on the top, and that's because nothing flats the surface. You can think of again like icing on the cake. When you put them, there's always this tip on the top, either coming from the breakup or the spreads. Nothing can flat the surface in the middle, but we don't see it in our experiments. The reason being that surface tension in these length scales are large enough to flat the surface in the middle.
So I think, are there any thixotropic effects?
At least not a strong thixotropic effect for the Carbopol we used. So we didn't see any, or at least within the time scale we did the experiments. No, we didn't see any thixotropic effects. But a spreading of thixotropic effects in smaller scale and also larger scale is important and nice. There is a paper by Neil Bamford and Duncan Hewitt on larger scale thixotropic spreading in Jane and FM. So maybe that's a nice place to start if you're interested in the topic. But for our materials, no, we haven't seen any significant thixotropic.
I think this is a follow-up question on the normal stress, asking if the hydrogel is impacted on the hydrophobic substrate and resulted in rebounding phenomena. What's the governing parameter?
Yes, then elasticity, normal stress, those become important. Yes, so because again, these materials, in particular, if you're in the regime that you don't yield everywhere or you don't yield them at all, then elastic properties or normal those things become important. Yes. If I'm not mistaken, I recently saw a JFM paper on viscoplastic droplets on superhydrophobic surfaces, but I might be mistaken about the context. But also very interesting direction to go and see the other parameters like effect of Deborah number on the rebound.
Hello, thank you for the nice talk. So my question was about a plateau, like the last picture. It looks the top of the drop is rather flat. If there is a nozzle, the surface will want to get pulled up, but the opposite is happening here. It looks a bit.
Okay. So the nozzle that we're using is hydrophobic. So the nozzle, actually, we intentionally chose a particular plastic nozzle that does not let the liquid wet the. It does a little bit, as you can see right in here. It's very tiny, but also here. It's because of the choice of the nozzle. So we intentionally chose a hydrophobic nozzle.